Here's lesson 2 of the quadratics unit. This lesson is on quadratics in vertex form. In lesson 1, I showed you the very basics of quadratics. You learned that the simplest quadratic relationship is this equation y equals x squared, and after making a table of values for it, we saw that its graph is this U shape that we call a parabola. And for the rest of the first lesson, we focused on quadratics in standard form, which are useful because the a value tells us the direction of opening, and the c value tells us the y-intercept. But there are two other formats that a quadratic equation can be in. They can be in vertex form or factored form. Each of those formats are good for different reasons because they reveal different key properties of quadratic relationships. In this lesson, we're going to focus on vertex form. You'll be able to recognize a vertex form equation because you have a binomial that is being squared, and then you have some constant values, a, h, and k, that are causing transformations to the x squared function. The a value is always multiplied in front of the power, the k value is always added after the power, and the h value is always subtracted from x in the base of the power. What I want you to understand by the end of this lesson is how these three parameters, a, h, and k, how they transform this y equals x squared function and how they manipulate its graph. It's going to cause some shifts up, down, left, right, and also some stretches and compressions and reflections. So one by one, let's go through and let's manipulate these a, h, and k values and see how they change the graph of y equals x squared. So the first one we'll start by manipulating the k value. The k value is always added after the power. And in this table, you'll notice that I've started by giving you the graph of y equals x squared, and then what we want to do is we want to graph this transformed quadratic equation, and then state some properties of it, including the vertex, axis of symmetry, and state what transformations we see have happened. So first of all, in these two equations that we have here, I see that we have an x squared function, and to those x squared functions, I have these values being added or subtracted after the power. Because they're after the power, I know that they're k values. So for the first equation, I can see that the k value is 3, and for the second equation, I can see that the k value is -2. Let's go into Desmos, and let's see what those k values do to transform the graph of y equals x squared. So I've got the graph of y equals x squared in behind the red function in black there, and then the red function on top is going to be our transformed function. So notice, if I make the k value 3, watch what happens to the transformed red function. If I make k value 3, all of the points seem to have moved 3 points higher. And if I make k -2, notice all of the points have shifted 2 units down. So the k value just shifts the function up and down. And I can sketch the graphs of these transformed quadratic functions by starting by plotting some points on y equals x squared. I'll just do points when x is -1, 0, and 1. And then for a k value of 3, I saw that the parabola shifted up 3. So I just have to take those 3 points and shift all of them up 1, 2, 3 units. And then connecting them gives me my transformed quadratic. Notice the vertex of this quadratic is now at the point 0, 3. And the axis of symmetry is the vertical line that goes through the vertex of that parabola. The equation of any vertical line is x equals whatever the x-coordinate of all of the points that are on this line are. All of the x-coordinates of the points that make up that axis of symmetry, all of their x-coordinates are 0. So the equation of the axis of symmetry is x equals 0. And the transformations that have happened, the quadratic shifted up 3 units. And then when k was -2, that's going to move all of the points down 2. So I'll take those 3 points and move them all down 1, 2 units. And then connecting the points, I get my transformed quadratic, which has been shifted down 2 units. Its vertex is now down here at the point 0, -2, and its axis of symmetry, the vertical line that goes through its vertex, is still at x equals 0. And now let's move on and look at how the parameter h transforms a quadratic equation. Remember, h is being subtracted from x in the base of the power. So in these two equations, let's look at what the h values are by determining what is being subtracted from the x value in the base of the power. Well, in this first equation, we see that 2 is being subtracted from x, so the h value is 2. And in the second equation, we see it says x plus 3 in the base of the power, but our job is to figure out what is being subtracted from x. So we could think of this equation as being y equals x minus negative 3 being squared. And that's equivalent to the line above because subtracting a negative is equivalent to adding, but it reveals that what we're subtracting from x is actually a negative 3, which means the h value for that equation is negative 3. And you may be noticing that the h value just has the opposite sign of what you see inside the brackets. If we see x minus 2, the h value is positive 2. And if we see x plus 3, the h value is negative 3. And now let's go into Desmos and see how varying these h values is going to affect the graph of y equals x squared. If I make the h value 2, notice that all of the points just shift 2 units to the right. And then if I make the h value negative 3, notice that all of these points are just going to move 3 units to the left. So the h value causes the quadratic to shift left and right. When the h value was 2, it shifted the quadratic 2 units to the right. So I can take a few points that are on the graph of y equals x squared, and then just shift them all 1, 2 units to the right. And then connecting them gives me the graph of my transformed quadratic. Its vertex is now at the point 2, 0. And since the axis of symmetry always goes through the vertex, I know that the x-coordinate of all of the points on that axis of symmetry are going to be 2, since the x-coordinate of the vertex is 2, meaning the equation of the axis of symmetry is the vertical line x equals 2. And then when h was negative 3 in the second equation, we saw that that shifted the parabola 3 units to the left. So I can take a few points on the graph of y equals x squared and just shift them all 1, 2, 3 units to the left. And then connecting the points, I have the graph of my transformed quadratic. Its vertex is now at the point negative 3, 0, and its axis of symmetry, which is the vertical line through the vertex, is now at x equals negative 3. Hopefully you're seeing the connection that the equation of the axis of symmetry is always x equals the x-coordinate of the vertex, and that's because the axis of symmetry is a vertical line that goes through the vertex. And now lastly, let's look at what happens when we manipulate the a parameter. Remember, a is being multiplied in front of the power. So in these two equations, we have two different a values. I have an a value of 2 and an a value of a half. And then there's actually a third equation below where we have a negative a value. We have an a value of negative a half. So let's go into Desmos and let's see what happens if we manipulate those a parameters. If I make a 2, notice that there is a vertical stretch by a factor of 2. All of the points are now twice as high above the x-axis. And if I make a half, that causes a vertical compression by a factor of a half. All of the points are now half as high above the x-axis. But if I make a negative a half, so if I throw a negative in front of that a parameter, notice that flips the parabola upside down. It's now opening down, so it causes a vertical reflection. So when a was 2, what happened was a vertical stretch by a factor of 2. And what that means, if I take a few points on the graph of y equals x squared, it means that their y values are doubling. So I need to take the y value of each of these points and double it. The y value of this first point is 1. If I double it, that brings the y coordinate of that point up to 2. And same with this point here. Its y value is 1, so I need to double it, making its y value 2. And this point here, its y value is 0, so when we double that, it's still 0. So connecting these points gives me the graph of y equals 2x squared. Notice anytime there's a vertical stretch, it's going to look like the parabola becomes thinner. Stretching that quadratic, though, does not change the location of its vertex. The vertex is still at the point 0, 0, which means its axis of symmetry is still at the vertical line x equals 0. And when a was a half, that caused a vertical compression by a factor of a half, which means if I take a few points on the graph of y equals x squared, I'm going to have to cut all of the y values in half. The y values of these 2 points are both 4, so when I cut them in half, they're both going to become 2. And the y values of these 2 points are 1. When I cut them in half, they become a half. All of the points are now half the distance from the y-axis that they used to be, causing a vertical compression. The vertex is still at 0, 0, and the axis of symmetry is still at x equals 0. And then lastly, we have y equals negative a half x squared. The only difference from y equals a half x squared to negative a half x squared is this negative value. And that's just going to change the sign of all the y values. So we can just take all of the points that made up a half x squared and change the sign of all the y values. So when x is negative 2 and 2, instead of having a y value of 2, the y values are going to be at negative 2. And then at x equals negative 1 and 1, instead of the y values being a half, they're going to be negative a half. And the vertex is still in the same spot. And then connecting them, I have my transformed function, which has still been vertically compressed by a factor of a half, but it's also being vertically reflected. Its vertex is still at 0, 0, and its axis of symmetry is still at x equals 0. And now let's summarize everything we found out in this investigation in this table here. Starting with how the a parameter affects the graph of y equals x squared. Remember, a is always going to be multiplied in front of the power, and if that a value is greater than 0, just like standard form, that's going to mean the parabola opens up. And if a is less than 0, that's going to cause a vertical reflection in the x-axis, which is going to make the parabola open down. And then remember, a can also cause stretches and compressions. If a is bigger than 1 or less than negative 1, it causes a vertical stretch by a factor of the absolute value of a. And if a is between negative 1 and 1, there is a vertical compression by a factor of the absolute value of a. And sometimes it helps people if I draw a number line to summarize this. If the a value is between negative 1 and 1, well, multiplying y values by a number between negative 1 and 1 is going to make them closer to 0. So it's going to cause a vertical compression. Now, of course, the a value can't be 0 because that would make the relationship linear, but that goes without saying. And if the a value is bigger than 1, or less than negative 1, that's going to make the y values further from the x-axis, causing a vertical stretch. And if a is greater than 0, the parabola opens up, but if it's less than 0, it opens down. So hopefully that chart is a good summary of how the a value transforms the y equals x squared function. And now let's look at h and k. Remember, h is what we're subtracting from x. So if we're subtracting a number bigger than 0, that's going to cause the parabola to shift to the right h units. But if h is less than 0, for subtracting a negative number, it's going to cause the parabola to shift left. And the k value, which is added after the power, if k is positive, the parabola will shift up. And if k is negative, then the parabola will shift down. And because h and k are what cause the parabola to shift left and right, up and down, that's going to change the location of the vertex. The vertex is always going to be at h, k. The h value becomes the x coordinate of the vertex, and the k value becomes the y coordinate of the vertex. And then the axis of symmetry is always going to be at x equals the x coordinate of the vertex, which is h. And for quadratic functions, the domain, which means the values x can take, is always going to be any real number, which just means for any quadratic equation, you can input any real number you want for x, and it'll be able to output a value of y. But the range, which means the values y can take, quadratic equations can't output any value. They're limited by their vertex. If the parabola opens up, the y-coordinates will always be at the y-coordinate of the vertex, or above, but if the parabola opens down, the y-coordinates of all the points that make up that graph will always be at the y-coordinate of the vertex, or below. And we'll learn how to write that in the table below. So for example 1, it says for each of these following functions, describe the transformations compared to y equals x squared, complete the table of properties, and then graph the function by making a table of values. So I can tell that this quadratic relationship is in vertex form because we have a binomial that is being squared. And then I see two parameters that are transforming that x squared function. This negative 3 is in front of the power, so that means that that's the a value. So I can say the a value is negative 3. And this parameter here is inside the base of the power, so that's the h value. Now, the h is always what we're subtracting from x. So since it says x plus 2, I know that means that we must be subtracting a negative 2 from the x to make it appear as x plus 2. So the h is actually negative 2. And then let's describe what transformations those parameters do to the graph of y equals x squared. Well, if we look back up to what I wrote before, if we look at this number line, an a value of -3 causes a vertical stretch and it causes the parabola to open down. So let's communicate that on this example. An a value of -3 causes a vertical stretch by a factor of 3. Notice I used the absolute value of -3 to describe the stretch factor. But because the a value is negative, it's also going to cause the parabola to open down. So I could say there's a vertical reflection, or I could just state that it now opens down. The h value of -2 is going to cause the parabola to shift left 2 units. And now let's fill out the table of properties. Firstly, the vertex. The vertex is always equal to hk. So h is -2, but what's the k value? Well, in this equation here, I don't see anything added after the power, so I could imagine that there is a +0 after. So this parabola hasn't been shifted up or down at all, so the y-coordinate of the vertex is still going to be 0. The axis of symmetry is always x equals the h value, which is the x-coordinate of the vertex, so x equals -2. And the direction of opening, since the a value is negative, I know it opens down. Values x may take, well, into this equation, I could input anything I want for x and be able to get an output of y. So for x, we say that x is an element of all real numbers. But for values y may take, let's actually wait to fill that out until after I've graphed the parabola. And to graph it, let's make a table of values. And because I know this parabola will make a U-shape, a parabola, I want points on both sides of the vertex. So I'm going to start by centering the vertex in the middle of the table. And then I could plot that point on my graph. And since this parabola opens down, I know it's going to look something like this. So I want points on both sides of the vertex. So I'll choose x values to the left of -2. So I'll choose -3 and -4. And then x values to the right of -2, -1, and 0. And then I'll sub these points into this equation and calculate the y values. If I sub in -3 in for x, I would calculate the y value to be -3. And if I sub in -4 for this x value, I get a y-coordinate of -12, which doesn't fit on my graph, but that's okay. And then subbing in -1 and 0 for this x value, you're going to see that I just get these two y values repeated again. And that's because parabolas are symmetrical on either side of the vertex. So if one to the left of the vertex, we have a point that's at a y value of -3, then one to the right of the vertex, there's going to be a point at the exact same y value. And then I can connect these. And now I should be able to answer the range of this function. What values can y output for this function? So looking at the y values of the points that make up this function, notice this point has the biggest y value the function can ever have, and the y value of that point is 0. So we say y can be any real number such that, or given, y is less than or equal to 0. All of the points that make up this parabola have y-coordinates that are less than or equal to 0. That vertex is the highest that parabola ever goes. Let's try another one. In part B, we have the equation y equals 2x squared minus 5. It may not look like vertex form, but we can consider it to be in vertex form if I were to rewrite it as 2 times x minus 0 being squared minus 5. But since the h value is 0, of course we wouldn't have to write x minus 0, which is why it just appears as an x that's being squared. And notice the two parameters that we have transforming x squared are an a value of 2. I know it's an a value because it's being multiplied in front of the power. And a k value of -5. I know that's k because it's being subtracted after the power. An a value of 2 causes a vertical stretch by a factor of 2. And a k value of -5 causes the parabola to shift down 5 units. The vertex is at hk, so in this case it's at 0, -5. The axis of symmetry is at x equals the h value, so x equals 0, right? It hasn't shifted left or right at all. Since a is positive, I know it opens up. Values x may take, for any quadratic, x can be any real number. But for the range, the values y may take, let's wait until we graph it. And to do its graph, I'll start by making a table of values by taking the vertex and putting it in the center of the table of values. I'll then want some points to the left and to the right. So to the left of 0, I'll choose -1 and -2. And then to the right of 0, I'll choose 1 and 2. And then taking these x values and subbing them in for the x in this equation, I can calculate their corresponding y's. Subbing in 1 for this x, I get 2 times 1 squared, which is 2, minus 5 is -3. So if one to the right of the vertex, the point is at a height of -3, one to the left of the vertex, it will also be at a height of -3. And then when subbing in 2 for this x, I get 2 times 2 squared, which is 8, minus 5 is 3. So 2 to the right of the vertex, it's at a height of 3. So 2 to the left of the vertex, it'll also be at a height of 3. And then I can connect the points. And having that graph will make it obvious what values y can take for this relationship. The y values are always at the vertex or above. So the y values can be any real number given that the y values are greater than or equal to -5. And let's fill out one more part for this question. Part C. This one we have all three parameters transforming the y equals x squared function. We have an a value of 2, causing a vertical stretch by a factor of 2. The h value is what we're subtracting from x in the base of the power. We're subtracting 3, so the h value is 3, which means the parabola is shifted 3 units right. And then the k value is 1, which means shift up 1 unit. So since y equals x squared, which roughly looks like this with its vertex at the origin, since it has been shifted right 3 units and then up 1 unit, its vertex is now going to be at the point 3, 1 instead of at 0, 0. Right, the h and k values become the x and y coordinates of the vertex. And the axis of symmetry will be at x equals h, which is x equals 3. Since a is positive, it opens up. X can always be any real number. And once again, we'll fill out the range after we graph it. And to graph it, I'll start by taking the vertex, putting it in the center of the table of values. And then I have to pick some points to the right of the vertex. So to the right of 3 would be 4 and 5. And then also to the left of the vertex, I'll choose x values of 2 and 1. And then just take all of those values and sub them into this equation. And then from this graph, I can see that the y values of this parabola are always at the y coordinate of the vertex 1 or above. So I'll say y can be any real number given y is greater than or equal to 1. And now let's do a question where we do a bit of the opposite. This time I'm going to describe the graph to you and we come up with the vertex form equation. Remember, the vertex form equation always looks like this. Y equals a times x minus h squared plus k. And now let's see which of those three parameters the question gives us. It says that the vertex of the parabola is at 1, 5. Well, remember, the vertex is the h and k values of the vertex form equation. And it also says it passes through this point 0, 2. So let's go into Desmos and see what we have so far. Well, I know the vertex is at 1, 5, so the h value is 1 and the k value is 5. But it also says the parabola passes through the point 0, 2. So let me plot that on the graph here. So how am I going to get this parabola to pass through that green point? We're going to have to solve for what value of a is going to make this parabola go through that point 0, 2. And I can see that if a was -3, it would now pass through that point that I want it to pass through. So we're going to have to algebraically solve for that a value of -3. And how we're going to do that is by taking this point that we know we want it to go through, that point 0, 2, and subbing that in for x and y into our vertex form equation, and then solving for a. So let me sub in these 4 parameters for x, y, h, and k into this equation, and then our only unknown is going to be a. And then solving for that a value, 0 minus 1 is -1, and then squaring that, I get 1. So I have 2 equals a times 1, which is just a, plus 5. Subtract this 5 to the other side. 2 minus 5 is equal to our a value, which means a is -3. So to write the final vertex form equation, you just have to sub in the a, h, and k values into vertex form. So I'll make a bit of room and do that. The final answer will be y equals -3, x minus 1 squared plus 5. And there's the final vertex form equation that defines all of the xy points that make up the graph of this parabola. And now let's do the same thing for example 3. This time, instead of describing the graph, I just show you a picture of it. When we're writing the vertex form equation of a parabola from its graph, you always want to start by picking out the coordinates of the vertex of the parabola. So this first one, I can see that the vertex is at the point -2, 4. That's going to be my h and my k values. And then to solve for the correct a value, we need one other point that is on the graph of this parabola. I see this point right here is the point 1, 1. That can be an xy point that will help me solve for the value of a. So into a vertex form equation, I can sub in for h and k, x and y, and then just be left with a to solve for. Solving this equation for a, following the correct order of operations, I'll start inside the brackets. 1 minus -2 is 3. Square that, I get 9. So I have 1 equals 9a plus 4. I'll subtract this 4 to the other side. 1 minus 4 is -3. And then dividing the 9 to the other side, I have a equals -3 over 9, which reduces to -1 over 3. So I can write the final vertex form equation by subbing in the a value, the h value. The h value, remember, was -2, so it's x minus -2. But you would never write x minus -2. We could simplify that to x plus 2 squared plus the k value of 4. So there's the final equation that defines all of the points that make up the graph of this parabola. And now let's do one more question like this. For the graph of this parabola, let's find its vertex form equation. Starting by looking at its vertex, I see the vertex is at the point 3, -1. So that is the h and k value. And then I need one other point, which I see this point right there is at the point 5, 3. That can be an xy point that is on the graph of the parabola. So into the vertex form equation, I can sub in for h and k and x and y, and then solve for a. Solving for a, I'll do 5 minus 3, which is 2, and then squaring it to get 4. So I have 3 equals 4a minus 1. Add this 1 to the other side, giving me 4 equals 4a. And 4 times 1 is 4, so my a value must be 1. So my final vertex form equation, if the a value is 1, you don't have to write it. I suppose we could write 1 times x minus h, so x minus 3 squared, plus the k value of -1, so minus 1. But a factor of 1 doesn't have to be written, so I could erase it. And there's my final vertex form equation for the graph of that parabola. Let's do a couple more questions to finish off this lesson. Example 4, it just describes the transformations in words, and then I have to figure out, based on the description, what are the a, h, and k values. And then I'll sub those into the vertex form equation. Well, it says the graph of y equals x squared is reflected vertically in the x-axis, so I know the a value has to be negative, and it's also compressed vertically by a factor of 1/4. So the a value has to be -1/4. It's also shifted 1 unit to the left, which means the h value is -1, and 2 units down, which means the k value is -2. So subbing those values into my vertex form equation, I have y equals -1/4, x minus -1, subtracting a -1 is the same as adding 1, squared, plus -2, so I can write -2. And there's the equation that defines the quadratic that's described in this question. And we'll finish this lesson with an application question. It says, at a fireworks display, a firework is launched from a height of 2 meters above the ground and reaches a max height of 40 meters at a horizontal distance of 10 meters. So before I read any further, I'm going to start to sketch what the question tells me. It's talking about the height of a firework, and it describes its height based on its horizontal distance from where it is launched. It says that it's launched from a height of 2 meters above the ground. So I'll start by plotting a point right here that's at a height of 2 meters. And then it says it reaches a maximum height of 40 meters at a horizontal distance of 10 meters. So at a horizontal distance of 10 meters, it reaches its max height, which is 40 meters above the ground. So this vertex is at the point 10, 40. And all projectile motion, the object is going to go up, it's going to reach its max height, and then it's going to start to come back down. But what the question says, it only travels 1 additional meter horizontally after it reaches its max height before it explodes. So it's going to get to some point right here where it explodes. So there's going to be an explosion at that point. It says, what is the height when it explodes? So I want to know, what is that height at the point where it explodes? Well, I know its horizontal distance. It says it goes 1 meter horizontally after the vertex, so its horizontal distance is 11. So this point is 11 something. Our goal is to just figure out that something, figure out the height of that firework when it explodes. Well, to do that, we need to generate an equation that tells us the height based on any horizontal distance that firework has traveled. Since I know the vertex and one other point on the graph of this parabola, I could write the vertex form equation. Vertex form equation usually looks like this: y equals a times x minus h squared plus k. Notice the height is the dependent variable, it's on the y-axis, and the horizontal distance is on the x-axis. So in this equation, know that y is height and x is horizontal distance. I've got the vertex, which can be h and k, and I've got this y-intercept here, the point 0, 2, that can be an x and a y value. Subbing that in to this vertex form equation, my only unknown would be a. Solving for a, I have a negative 10 being squared, that's 100. I'll subtract this 40 to the other side. 2 minus 40 is negative 38. And then dividing that 100 to the other side, I see that a is equal to negative 38 over 100, which reduces to negative 19 over 50. So now I can actually write the vertex form equation of this quadratic relationship. The height, y, is equal to negative 19 over 50 times the horizontal distance, x, minus 10 squared plus 40. And I want to know, what is the y value? What is the height when x is 11? So I can just sub in 11 for this x and solve. And if I evaluate this, I get a y value of 39.62 meters. So that is the height when the firework explodes. So hopefully now that we're at the end of this lesson, you have a good understanding of the vertex form equation of a parabola. Make sure to go to jensenmath.ca so you can get a copy of the free worksheet that goes along with this lesson and try out the practice problems. Jensen